Okay, for anyone who missed the lecture I did in class about series and parallel circuits, I'm going to recreate it right now. So let's go write this up right up here: series and parallel circuits. And we're going to start by talking about the series circuits because they're the easiest. So I'm going to draw myself a series circuit. Let's do that. Let's draw a battery. And it's going to be a 12-volt battery, and this is going to be the positive terminal up here. And now I'm going to make a schematic where I have one resistor on this leg, one resistor on this leg, and one resistor on that leg. I'm going to mark these corners and label them A, B, C, and D, and each of these is going to be a 4 ohm resistor. Ooh, my omegas are getting a little out of control. Okay, so how do we handle this situation? We have multiple resistors to deal with. Well, first thing I need to do is introduce a concept of the equivalent resistance. In other words, there is one single number for resistance that is the same as having 3 4 ohm resistors in a row in series. And why is this in series? It's in series because if you're a little charge dude coming out of the battery, you have to go through each of these resistors in turn. There are no choices, no forks in the road. So you go through one, then the other, then the other. Series is an and proposition. You go through this resistor and this resistor and this resistor. There's no or here. And the equivalent resistance in this situation is so simple. It is simply the sum of all the resistors. So since we have 3, I would write that. If we had more, we could keep going. So in this case, the equivalent resistance is going to be 4 plus 4 plus 4, or a big old whopping 12 ohms of resistance. So does that mean that these 4 ohm resistors, all 3 of them, are somehow equal to one 12 ohm resistor? Could we draw a little tiny circuit over here with a battery and then just one resistor and label this 12 volts and 12 ohms? Well, in some sense, this is an equivalent circuit to that. From the perspective of the battery, it is the same difficulty to shove charges out through this circuit as it is through this circuit. Now, there is some difference. Obviously, this has got 3 resistors. This only has 1. These 3 resistors might be 3 totally different things in a circuit. You know, a light bulb, a blender, and a car horn. You know, that might be the case. And this can't be all 3 of those. But to the perspective of the battery and to the perspective of how much current flows, they're the same. And in fact, that's the next step. You see, this whole thing is predicated on the idea that you use Ohm's law once for the whole circuit and once for each individual resistor. So let's find the current that comes out of the battery. The current that comes out of the battery and goes around. It will be the current that is the same everywhere in this circuit through each of these resistors because there are no other choices. The current that comes out of the battery is the voltage of the battery divided by the equivalent resistance, which in this case is 12 divided by 12, or a big old whopping 1 amp. So already we've done the equivalent resistance for this circuit, and we figured out how much current flows. And if we know how much current flows through each of these resistors, we can work out how much voltage each of these resistors will dissipate. Let's do that right down here. What about the first resistor? Well, the current from the battery times its resistance will be equal to 1 times 4, or 4 volts. Number 2 is the same. The current from the battery times its resistance. Now you can see that if these were different size resistors, I'd be getting different results, but I'm not because I made a simple circuit for me. So there we go. Each of these resistors is going to dissipate, consume, or otherwise eat 4 volts. And a very interesting thing happens. By the way, there's 2 ways to think about voltage. One is how much energy or voltage is dissipated in each resistor, and the other thing is how much voltage is left over. In other words, coming out of the battery, when the charges go around point A, How much voltage do they have? Well, they have 12 because they haven't gone through any resistors yet. But then after they go through this resistor after A, between A and B, they're going to lose 4. So by the time they get to B, they're going to be down to 8 volts. They're going to lose 4 more between B and C. So by the time they get to C, they're going to be down to 4 volts. And then they're going to lose 4 more as they go from C to D. So by the time they get to D, they're going to have 0 volts. And so the two different ways to think about voltage, that is voltage consumed and voltage left over, are totally consistent with each other, right? We always start with the voltage of the battery. We always go home with 0 volts. That's the rules. And then each of these resistors is responsible for consuming some voltage. So we did Ohm's law for the whole circuit to find the current. We did Ohm's law for each resistor to find the voltages. And that's how you handle series circuits. So let's do one more, and let's do it on a circuit that doesn't have all the same resistor. Okay, just remember what we did here and where we did it. So let me draw another circuit. We're going to stay with our 12-volt battery. And we're going to have 3 resistors again. And this pen really is only for shading at this point. In fact, I'm going to put it in my drawer. There we go. Ha-ha. So let's do a 4 ohm resistor, an 8 ohm resistor, and a 12 ohm resistor. Hopefully I got this right. And we can also do points A, B, C, and D. Okay, using the same color scheme as before, the equivalent resistance is the first thing we find. And it's going to be R1 plus R2 plus R3, which is going to be 4 plus 8 plus 12. Let's see, 8 and 12 is 20, 24, 24 ohms. Okay, cool. Next, using the green pen for the current, I'm going to find the current that comes out of the battery using Ohm's second law, which is the voltage of the battery divided by the equivalent resistance. And that's going to be 12 divided by 24. Hey, we're looking at half an amp of current. So half an amp of current through each of these guys. I'll put a little arrow here to say 0.5 amps. Now we'll get out the blue pen and we're going to find the voltage dissipated by resistor number 1, which is the current, times resistance number 1, which is 0.5 times 4. This guy only eats 2 volts. 0.5 times 8. This guy's going to eat 4 volts. Bet I know what's going to happen next. 0.5 times 12, 6 volts. And notice 6, 4, and 2 add back up to my 12 volts. All the volts of the battery have been consumed. And if you'd like to know what the voltages are at the various places, VA, 12 volts, because that's right outside the battery. No resistors have been gone through yet. Then we go through the first resistor, we lose 2, so the voltage at point B, 10 volts. Then we go through this resistor, we lose 4, so the voltage at point C, 6 volts. Then we go through this last resistor and we lose 6 volts, and we go home with 0 volts. Happy birthday. This is how to solve the crap out of a series circuit. Now, I'm going to draw one for you guys to play with, and you can pause the video and see what you can do. And tell you what, we don't need to do the voltage at the various things. We're just going to do everything above the black line. And I want you to do it for this circuit. 12-volt battery. Okay, so we're going to have a 6 ohm and a 2 ohm and a 4 ohm and a 4 ohm and a 3 ohm. Oh, that's a bad looking one. And a 5 ohm. I should slow down. They look a lot better when I slow down. Okay, your job is to find REQ. I want you to find the current coming out of the battery, and I want you to find the voltage 1 through 6 for each of these 6 resistors. Go ahead and pause the video at this point and see what you can do. So next up is going to be parallel circuits, and they're very, very different. A parallel circuit is more of an or proposition. There will be forks in the road. So to draw one, you need to extend out the wires on the top and bottom of the battery, 12-volt battery, and then you're going to start connecting the top and bottom wires with resistors. And we're going to make these all 12 ohm resistors. So, very different. If we were to trace the charges as they come out of the battery, when they hit this spot right here, they have to make a decision. Some of them are going to go down through this resistor, some of them are continuing on. The ones that continue on, when they reach this point, they have to make a decision. Do they go down this way or do they continue on? If they continue on, they have to go around this way. And when these guys go around the corner and they get down here, they meet up with their friends that came this way. And then these guys all meet together with their friends that went this way, and they all go back home to the battery. So this is a question of going through this resistor or this resistor or this resistor. Another thing I want to point out here, and that is that all along this top wire, the charges have 12 volts of energy because they have not yet gone through a resistor. All along the bottom wire, they must have 0 volts of electricity or voltage or energy because they are about to go home to the battery. So each of these resistors actually consumes 12 volts. We know that they have the same voltage on them. They just might have different currents. So this is where we run into a little bit of trouble. The equivalent resistance for a parallel circuit is a little odd. It is the opposite of a series circuit. It is the reciprocal. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3, and if there were more, you would continue going. Now this is the actual law, and you can write this down. That's for a parallel circuit. But a lot of people don't like this because it doesn't solve for Req. It solves for 1 over Req. So let me give you a version that works pretty well. Do the stuff in parentheses, then invert the answer, and there you go. In this case, Req is going to be 1/12 plus 1/12 plus 1/12, which is going to be 3/12. That's how fractions work, which is going to be 12 over 3. So Req is going to be 4 ohms. Interesting, I have 3 resistors, each of which is 12. And when I combine them, I get less resistance. Yep, that's how parallel circuits work. And unlike series circuits where you combine more resistors, you get more resistance. In parallel circuits, when you combine more resistors, you get less resistance. If you get less resistance, you get more current flowing. So I imagine more current will flow in this circuit than did in any of our series circuits. So let's work that out. The current out of the battery is equal to the voltage of the battery divided by the equivalent resistance. So 12 divided by 4 is 3 amps. We've got 4 ohms. We've got 3 amps coming out of this battery. Now, this 3 amps is going to split up and go 3 different ways. It looks like it's going to go 1, 1, 1 because these are even, but we need to be proving that. So instead of solving for the voltages in a parallel circuit, you solve for the currents. The current through resistor 1 is the voltage, which is 12 volts, as we said before, divided by resistor 1. So 12 divided by 12, or 1 amp. The current through resistor 2, voltage over resistor 2, 12 over 12, 1 amp. And the current through resistor 3, 12 over 12, 1 amp. And these three add back up to the current out of the battery, which is 3 amps. So now we know that each of these has 1 amp of current going through it, 12 volts of voltage across it, they say, or being consumed by it, and has a resistance of 12 ohms. Yeah, voltage across is something that we say quite a bit. All right, let's do one more of these, and then we'll summarize, and we'll talk about what we're going to do next time. So just a quick recap here, because we find the equivalent resistance, but it's a little harder. We find the current out of the battery, and then we find the individual currents because the voltages are already known to be the same. Okay, I picked one for you that's a little more challenging. Battery, long wires. The one on the end is 6 ohms. The next one in is only 4 ohms, and the next one in was the original 12 ohm guy. Okay, REQ, 1 over R1 plus 1 over R2 plus 1 over R3 minus 1. Look, I'm in the habit of writing out the equations because I know that if the grader is looking at this, they're going to give me points for this, even if I now proceed to put the wrong numbers in. So I'm just so used to trying to get maximum partial credit. 1 over 12 plus 1 over 4 plus 1 over 6. Oh, holy common denominator, Batman. Looks like 12 is a good common denominator, so let's see. That's 1 over 12 plus 3 over 12 plus 2 over 12. So that's a grand total of 6 over 12, or 2 ohms when you flip it over. All right, let's find the current out of the battery. 12 over 2, 6 amps. Ooh. By the way, this is what happened to Clark Griswold in the National Lampoon's Christmas Vacation. He kept plugging in Christmas lights more and more and more, and they're all being plugged in parallel. Resistance is dropping, current is increasing, until finally I don't remember whether he lit the house on fire or popped the circuit breaker or something. I know the Christmas tree lit on fire somewhere in that show. All right, now that we know we're going to have the same voltage on each of these guys, so let's find the currents through each of them. That's going to be V over R1, which is going to be 12 over 12. 1 amp is going through the first guy. Okay, 12 over 4. 3 amps is going through the second resistor. And 2 amps is going through the third resistor. And these add back up to 6 amps, so everything's right with the world. So, what did we learn today? Well, we learned that you use Ohm's law once for the whole circuit. Oh, this pen is going. And once for each resistor. We learned that in a series circuit, we have the same current everywhere, but we might have different voltages. We also learned that REQ for a series circuit is the simple sum of all the different resistors. We learned that for a parallel circuit, we have the same voltage for all the resistors, but we might have different currents. We also learned that the equivalent resistance is a reciprocal arrangement. And another thing that we kind of learned on the sly is that more resistors in parallel leads to more current. And your houses are wired in parallel, so this becomes important. All right, folks, good day of learning. I got this video to the 20-minute mark, so off we go.